The learning objectives for this video include naming cycloalkanes, cistrans isomerism, ring strain conformations of cycloalkanes, and in particular cyclohexane conformations. Ring structures are found in a diversity of organic compounds. Here are some examples in the prostaglandins and steroid categories. So here there's a 5-membered ring, and here we have a lot of different 6-membered rings. We've got 3 of those and a 5-membered ring. In naming cycloalkanes, we're still going to use our other rules, but we're going to use the prefix cyclo in front of the parent name to indicate that it's in a ring, not a linear chain. So if we have 3 carbons in a ring, that becomes cyclopropane, 4 carbons, cyclobutane, cyclopentane, and cyclohexane. So these are the ball and stick models, and these would be the representations on paper. They have the general formula CnH2n, where n is an integer. So notice for cyclopropane, it would be C3H6, where the number of H's is exactly twice the number of carbons. When you have a ring and you want to name it, you first want to find the parent. So the parent is either the ring or whatever is attached to the ring that has the greatest number of carbons. So for example, here, the substituent just has 1 carbon, it's a methyl group, but the ring has 5 carbons. So the parent is going to be the ring. So the parent name is cyclopentane, and then we have to indicate there is a methyl, so we write methyl in front of that. And when you have just 1 group on a ring, you don't have to assign it a number. Now let's look at this other example. We have a 3-carbon ring here, but then we have a 4-carbon chain. So the chain is actually going to be the parent. So the parent is butane, and then we name the ring as a substituent. So this would be cyclopropyl. Just like with methane becoming methyl when it's a substituent, cyclopropane becomes cyclopropyl when it's a substituent. When we have more than 1 substituent on a ring, we want to number the substituents to give everything the lowest possible number. So for example, if we have this 6-membered ring, the parent name would be cyclohexane, and we've got 2 methyls on it. So there's different ways we could number this. We could number clockwise or counterclockwise. So here is the clockwise, 1, 2, 3, 4, 5, 6. That would give the methyls at carbons 1 and 3. If we numbered the other direction, this direction, then the next substituent would not arrive until we get to carbon 5. So that number is higher than the 3, so this is the correct way to name it. If we look at this more complicated example, we want to number this ring so that the 3 substituents have the lowest possible number. So this is the correct way, where we have the methyl at 1 and 4 and the ethyl at 2. Notice with these other options that we have higher numbers than with the ideal correct name. So here we'd have the ethyl at 3, and here we would have one of the methyls at 6. So why don't you pause the video and see if you can name these groups on your own. So now we find the parent, which is indeed the cyclohexane. So we know the parent name is cyclohexane. Now we have to figure out the numbering. We could either number this 1, 2, 3, 4, 5, 6, or we could number this 1, 2, 3, 4, 5, 6. You always start numbering with a carbon that has a substituent. You never start numbering on a carbon that doesn't have any groups attached. So what would be the difference here? If I use the numbering in red, I would have a methyl at 1 and an isopropyl at 2. And when I assembled that into a name, the I would alphabetically be before the M, so that would become 2-isopropyl 1-methyl cyclohexane. Now if I use the numbering in green, I would have an isopropyl at 1 and a methyl at 2. And then that would become 1 isopropyl, 2 methyl, cyclohexane. So which one is correct? Because they both have the same low numbers. So in this case, you want to give the lower number to the one that comes alphabetically first. So you're going to choose this option. Now let's get a little more complicated. So here we have a 7, 1, 2, 3, 4, 5, 6, 7. So the parent name there is cycloheptane. And now I have to figure out my numbering. So I want to number so that I get the lowest possible numbers on everything. If I have two substituents close to each other, I'm going to number them first. So that would be 1, 2, 3, 4, 5, 6, 7. Now, what other ways could I number? If I numbered this way, 1, 2, 3, 4, 5, 6, 7, then I get the numbers 1, 2, and 6 for the substituents versus 1, 2, and 4. So that's not as good. I could also try numbering like 1, 2, 3, 4, 5, 6, 7. If I number the way I've numbered in green, then I get substituents at 1, 3, and 4, which is also not as good at 1, 2, and 4. So you might have to play with this a little bit and try different numbering schemes. One thing I always do is that if I have two substituents on carbons adjacent, I start with numbering those because I know I'll get numbers 1 and 2 if I go in that direction. And then I want to number in the direction that gives me the next substituent at the lowest possible number. So the way I've numbered in blue, I have a tert-butyl at 1. I have a methyl at 2. And then I have a bromine at 4. Which when it's a substituent, we call it bromo. So now if I assemble those in alphabetical order, we ignore the prefix tert when alphabetizing. I get 4 bromo, 1 tert butyl, 2 methyl, cycloheptane. And here are the solutions to that example. Cyclohexanes are less flexible than their open chain counterparts because they're locked into a ring, so they have a lot less freedom. So notice if you have ethane, you can freely rotate, but if you have cyclopropane, you could build the model and prove this to yourself. You can't freely rotate those carbon-carbon bonds. As a result of that restricted rotation, you can get what's called cis-trans isomerism. Any cycloalkane you can think of as having two faces. If you're looking down on this from above, there's the top face, and then if you're looking from below, that would be called the bottom face. So if you have two substituents that are both on the top face, then we call that cis. But if they're on different faces, we call that trans. So this would be an example where see both of the methyls are pointing up, but here one methyl is pointing up and one methyl is pointing down. Notice the wedge here, that's an indication that that carbon is coming out towards you. And then these would be the ball and stick representations. So cis and trans isomers are just examples of stereoisomers, which are isomers that have the same atom connectivity but a different three-dimensional geometry. Contrast that with constitutional isomers, which actually have a different atom connectivity. So here are some more examples. This would be cis 1,3-dimethyl-cyclobutane, and this would be trans 1-bromo-3-ethyl-cyclopentane. So notice you actually want to put the cis or trans stereochemistry at the beginning of the whole name when you name these. We can also get cis and trans isomers with double bonds, but we'll get to that in a later chapter. Cycloalkanes experience ring strain. Of the cycloalkanes, cyclohexane is the most stable, and in comparison, cyclopropane and cyclobutane are much less stable. The reason is because of angle strain, which is the strain resulting from deviation from ideal bond angles, and torsional strain, because we can actually get eclipsing conformations. So for an sp3 hybridized carbon, the ideal angle is 109.5. And a cyclopropane, it's really deviated from that at 60 degrees, and cyclobutane, it's 90. Cyclopentane's not too bad, it's very close. And then in cyclohexane, if you just draw it out flat, it would be 120. Cycloheptane, cyclooctane. Now these values are assuming the ring is flat. As it turns out, the ring isn't going to be flat. It's going to adopt slightly different conformations to minimize this angle strain and the torsional strain. In cyclopropane, the internal angles are 60 degrees apart, so there's significant angle strain. Also, you could actually draw a Newman projection of this if you're looking down one of these bonds, and you will see that there are eclipsing interactions amongst the CH bonds, which gives this molecule a lot of torsional strain. In cyclobutane, the internal angles are 88 degrees, and it will actually adopt a somewhat puckered form to alleviate some of the eclipsing interactions, because if it was flat, see how these CH bonds would all be lining up with each other? So it puckers to prevent that. Same thing happens with cyclopentane. It's not going to be flat because you would have all of these CH bonds just lined up right on top of each other. So it forms either what's called the envelope conformer or what we can call the twist conformer. So this moves the hydrogens out of their eclipsing interactions. Cyclopentane's actually pretty stable. It's just slightly less stable than cyclohexane. There's very little angle strain, and if it adopts one of those conformations like the envelope conformation, it avoids those eclipsing interactions, so there's only slight torsional strain. Now cyclohexane is the one that we're going to really spend a lot of time working with. It is going to exist in what we call the chair conformation, and you're going to learn how to draw these. We're going to draw lots of chairs. In the chair conformation, there's no angle strain and no torsional strain. And you could actually draw a Newman projection. So this Newman projection would be if you're looking down these bonds simultaneously. So these hydrogens would be these hydrogens here. These hydrogens would be these hydrogens. And then this carbon is this carbon. This carbon would be this carbon. And then these carbons would be these circles in the back. This is a cyclohexane, and now it's in what we call the chair conformer. So notice that that kind of looks like this lounge chair, which is why we got the name chair. Now if we look at the red atoms, those are what we call the axial atoms. They are on the top face of the ring and the bottom face of the ring, and they point up and down. Then the atoms in green we call the equatorial atoms, and they are facing out in the equatorial plane. So we can think of those positions as occupying the equatorial plane. Then these interactions are what we call 1,3 diaxial interactions, which we'll get into in the next video. Now, cyclohexane can adopt the chair conformation, and it can actually flip between two chair conformations. And when it does that, it goes through these intermediate conformations. And I will want you to be able to draw the different chair conformations when you do a ring flip. So in the boat conformer, it's called that because it bears a slight resemblance to a boat. And there's no angle strain, but there are a large number of eclipsing interactions. In the twist boat, that also is nearly free of angle strain and has slightly less eclipsing interactions. So here is the chair conformer, and it's going to go through a ring flip. So it goes through the half chair, into the twist boat, into the boat, into the twist boat, back into the half chair, and then into the chair. So notice the axial hydrogens are in red. Now we're going to do another ring flip. Half chair, twist boat, boat, twist boat, half chair. And now notice the red hydrogens are in the equatorial position. So whenever a cyclohexane undergoes a ring flip, the axial and equatorial positions switch. So if the atoms were axial, they'll be equatorial after a ring flip. And if the atoms were equatorial, they'll be axial after a ring flip. The final thing I want to talk about is how to draw the chair conformations. So here is a 5-step process. In the first one, you draw a wide V, and then in the second, you draw a line going down at a 60-degree angle, ending just before the center of the V. Then you draw a line parallel to the left side of the V, and then a parallel line to the line from step 2, and then you connect the dots. And there are different ways to do this, but this is one sequence of steps that I think works well. So you draw your V, then you draw this line, this line, this line, and then you connect the two. So that would be one chair conformation. And then if you do the flip, you would draw a different chair conformation. So you would start with the V, but then you would draw this line first, followed by this line, followed by that line to finish the chair. So one chair is going to kind of be pointed in that direction, and the other chair will be kind of pointed in the other direction. So if drawn correctly, the chair should contain 3 sets of parallel lines shown in red here. And each carbon in the ring has 2 substituents. One is in the axial position and the other is in the equatorial position. So in adding the axial substituents, those are the easiest. So after you draw your chair, you're just going to alternate with the corner here with an axial up stick, and then the next one axial down, and then you just alternate until you get all of your axial substituents. Then the equatorial groups are drawn off of the ring. They're harder to draw, but they're going to run parallel to the lines in the chair. So now the lines in blue show all of the equatorial bonds. So try practicing these chairs with the axial and equatorial bonds. And here's just another picture of a chair drawn with the axial and equatorial bonds. And that's it for this video.